So we should be recording now. So we're going to get started today with the class. Oh, yep. There you go. All right, so let's start a few things. Is, all right, so we're going to go to Brightspace, start here, just to kind of get a feel for where we are. 365. Let's go to content. Okay. So we are basically looking at these three modules right now. On Wednesday, we will start our first algorithm, KNN, the K-nearest neighbor algorithm, and we are going to implement this from scratch. So get your Anaconda environment ready to go. As usual, I provide the code already. You'll have on the GitHub, of course, but I'll go over the algorithm, and it's going to be your first machine learning algorithm. We're going to explore a lot of ideas. So that's usually what I'll try to do every week is one new algorithm. So KNN, hot-field networks, for the perceptron, multi-layer perceptron, all of those. So if you remember the course, the way that I divided it is in 3/3. Basic algorithms during the first third until the first exam, then neural networks and deep learning the second third, and then in the third, special topics and something called transfer learning, which you will learn about a little bit later. Okay, so we've talked about matrices and vectors and NumPy. As I said, I don't really have time to cover this, as it should be a bit of a review since you should have looked at this in 265. But go through all these problems, develop the muscle memory, and they will help you a lot to warm up to the code. Okay, as we use a lot of these techniques in the problems. We talked about the machine learning pipeline, and this is what we're going to do today. So word problems. Okay, no coding today. Just we're going to read like word problems, and how do we start thinking about converting a word problem into a machine learning compatible problem. Okay, so we'll go over these. Last week we covered Weka, and you can refer to that video if you don't remember. I went over these examples basically, and as you can see, I have added your first homework assignment. So that's what I'm going to talk about right now. Okay, before we begin, this assignment, as you can see, is due 2 weeks from today. Right? Any questions on that? All right, so let's go ahead and read through it. So I have basically the data sets. I decided to give you the data sets this semester. These are cybersecurity data sets, given that you're most of your cybersecurity students. And basically, one is a network security data set, because it's called KDD. It's a classic network security data set that was used in competitions, so it has been studied extensively. Software assurance, it's malware detection. I think is metadata, so it's not actually the malware itself, but the metadata about it. And then the social engineering is phishing, the phishing problem, and also it's a metadata problem. Okay. Does that make sense? So these data sets are bigger, so they're meant to be, a challenge. You have to clean them up a little bit, load them in Weka, and do the analysis. So basically what I did in class the last time. All of these are classification problems, if I remember correctly. And I made the distinction between classification and regression in the video, so hopefully you can refer back to that. That's a key concept that you need to understand, okay? Classification, predict if this image is a 1, a 2, or a 3, cat, dog, or whatever. Regression is, what is the temperature today? 72, 73, 73.5, and so on. So use 3 data sets from here, and I loaded these on the GitHub already. And I'll click on these in a sec, and perform a complete ML pipeline. So remember, when I say ML pipeline, I mean go from data all the way to training a model and doing the performance metrics of it, right? So I've shown you how to do that with Weka. For each data set, select at least 3 different models. What I mean by that is naive Bayes, KNN, multi-layer perceptron, 3 of them. Okay, I recommend that multi-layer perceptron be one of them. And the reason why is it takes a while to train these models sometimes, especially multi-layer perceptron. So I want you to understand that it takes time to train. Okay, and that's really important. So for each data set, select at least 3 different models and indicate which one is the best. And you should know how to do that just by looking at the performance metrics, basically. Also do feature ranking. If you remember, I explained this concept last week. It's in the video as well. And essentially, you're just telling me which features contribute the most. So you need to provide that ranking. And then please, when you submit a report. PDF or Word is fine with screenshots showing evidence that you did the work. Does that make sense, guys? And if this is individual work, is your first homework assignment, you have 2 weeks to work. Okay. All right. And this is what I'll be doing. So we're going to do a few algorithms. I may not do a homework for KNN, and instead we do a homework for hot-field networks. You see, so I'm going to, I'll pick the algorithm that I want you to do something with, but it's all leading up to, just understanding machine learning in general. Yeah, so that's the homework. So let's click on one of these. So these are actually, on my GitHub, I have files. You can ignore these Jupyter notebooks because they implement, let's say they implement something like anomaly detection or something, but it's written in Python, right? So this is going to be something that we might look at in the future. All you need is the CSV file for all of it. Okay, that's the only thing that you need because obviously your software will be the Weka GUI-based program. Okay, so notice that this file, you can either use only the train file and split it, that's fine, or challenge yourself to understand how to load the train file and then evaluate on the test file. I did mention this in the video. If you look somewhere in there, there's like 30 seconds that show you how to do that. I alluded to it. All right, but you can do that if you'd like. Go back. So that's the network security one. Then the software assurance, same thing. There's going to be a whole bunch of zip files, etc., for other things that I was doing there, but really all you need is the CSV file. There's only one, so there's no way you can get confused. Make sense? And for the last one, this one, the same thing, phishing.csv. That's the file that you need. So those 3 files, load them in Weka, run the machine learning pipeline for 3 algorithms, look at performance metrics, indicate which one's the best, do feature ranking. And that's the homework. Any questions before we move on? Okay, great. So sounds like it's clear. So now what we have on the agenda today, so let's go back to Brightspace. What we have on the agenda is this week, today I'm just doing word problems. So I'm going to use my whiteboard actually for that. But I think actually, although there's no coding in this lecture, it's actually really important. Okay, it's really important to learn how to think about this because, eventually you may go somewhere. Let's say you work at a factory and you're told, okay, build me a machine learning model for this, some kind of packaging thing. How do you even begin to solve that, right? So that's the goal of this. So I'm trying to give you a common methodology that you can follow and to at least arrive at the first iteration of solving the problem. And then from there, you just iterate. Okay? Got it? So that's what we're going to do. And then I hopefully that will cover today's lecture. And then on Wednesday, we would look at KNN. We're just going to start coding and look at the fun of understanding these algorithms from scratch. So that's one of I like to code these with NumPy, so it's pure, from scratch code. All right, so yeah, so that's the agenda. So we're gonna go through these 2 documents, and I may not create a homework assignment for this, given that I've already given you the Weka homework assignment. Okay, so, but problems like this will be on the exam on week 6, so make sure you understand the concepts. Before I begin with this, I wanted to make point out that the world of AI just keeps moving like crazy. I don't know if you guys know what has happened in the last week in the world of AI. No, not informed. No one? DeepSeek, right? DeepSeek, yes. Actually, two big things happened. On Monday, they announced that they wanted to spend $500 billion. $500 billion, but it's supposed to be a private thing on building the infrastructure to train AI. Think about that, like $500 billion. Just one data center. They're building two, I think, in Porter and but in Porter and Charleston. No, I forget the name, but anyway, by Valpo. And so basically they're built, and each one of these costs, I think, 1.6 billion for one data center. So $500 billion gives you what, 400 data centers? So they want to spend a lot of money, right? That was the first thing. Yeah, go ahead. So it's Porter or Portage, they're building one, I think, and that's Google, I think, Google or Microsoft. And the other one is they were looking at, forget the name, unfortunately, but it's by Valparaiso. Stock profit. Yeah, so that's where I'm going. So it's very funny because it's a coincidence that both things happen at the same time. So on Monday, they made the announcement, $500 billion, that's 500 billion. I think one data center is 1.6 billion. So that's 400 data centers throughout the United States for OpenAI. And then on, what was it, the 20th, DeepSeek came out, which you've heard of and you've heard of. So DeepSeek is basically a Chinese company, a financial services company. And apparently they trained an equivalent of ChatGPT right now, and they made it available for free for everyone to use. And they made huge breakthrough in the amount of GPUs apparently that they needed to train it. So for instance, ChatGPT costs, let's say, I don't want to exaggerate because they don't tell you, but $100 million, and they did it for $5. That's significant. And so, as you said, and what happened today, this morning when I checked, NVIDIA stock, which is the one that produces the NVIDIA GPUs, which everyone has needed, they dropped by 10%, wasn't it? Yeah, they've dropped significantly in market capitalization. So imagine, you've heard of real estate bubbles, right? Like houses are overpriced. In the AI sector is the same. All these companies, Microsoft, OpenAI, Google, have this cap. And now, especially NVIDIA, which has been rising a lot. I actually have a statistic on NVIDIA because I've been keeping track of them. You can see here in forecast. I have AI trends in NVIDIA revenue in billions. So actually, which one is NVIDIA? The red. So you can see it's gone up from maybe 5 billion over here, right? 5 billion to, what is that? 60 billion in less than 10 years. So from 5 to 60 billion, right? So in AI, because of AI, because every company like OpenAI, Microsoft. So for instance, if you think Elon Musk bought 700,000 GPUs, Meta bought 700,000 GPUs, because the idea with artificial intelligence is it requires a lot of GPUs. That's been the bottleneck. You need clusters of thousands of GPUs to train these foundational models, as they call them, and then they have all these other methods that they invent, and now the models can reason. which is very interesting. So it's like the model start, oh, this is a problem, and they're like, okay, I'm gonna break this down into this. And what if I do this? Oh, wait, no. And it keeps doing that until it arrives at a solution. So these models that are reasoning now, one of them is obviously ChatGPT, and they just dropped their DeepSeek R1, which can reason. It's as smart, it seems, as ChatGPT, but at a significantly lower cost. And just 4 days after the announcement of the $500 billion investment. So NVIDIA stock, which has been the only provider of GPUs, right, which is why you had to learn that whole matrix multiplication thing, because that's what the GPUs do efficient. And they are the only providers, so their market has been up, market cap, and now it's gone down. You had a question?
Yeah. So I don't think so that the AI have spent, billions upon billions on GPUs. But what about storage? How do they store all the data that they process to the AI? Don't they have to?
The AI is not storing the data. It's learning weights. So there's a vocabulary. Think of it as there's 50,000 words in a vocabulary. And what it learns is how to, given a few of those, what comes next. And it just like, you give me these, and it just like, you give me 1, 7, 3, 5, 67, and those are words, and it goes in, then it learns, okay, based on that, what follows is 8, 99, 52, 67, 55. That's all it's storing. And then those numbers get converted back into the equivalent word that they represent. So numbers go in in a sequence that represent, 1 7 is the, cat is 55, is 37, sleeping is 400. That goes in. What comes out is 52, 99, 8, and that means the cat is sleeping on the table. But it doesn't actually store like a database or anything like that. It just learns these sequences, but the network is massive. Like that's why they say 7 billion parameters, 300 billion parameters. It means literally 300 weights connecting this to that. We'll look at this when we look at neural network. So it's not actually, it's knowledge, but it's compressed knowledge. That's a good analogy. So you guys know that you can have an image, right? But when you compress it, you have other data in there via an algorithm, and then you can uncompress it, right? So these GPTs are a type of compression machine. They take knowledge, compress it in their own understanding of things, and then decompress out answers. So, I mean, yeah, essentially. Yeah, so that there's the storage, I wouldn't say it's such a big deal, but if you download a a model like this, it might be 2 gigs, just the network and the weights.
I was thinking more along
Yeah.
the lines of all the training
Well, that is, yeah, so here then, what probably happens is you have 1,000 GPUs, and every GPU will do some processing, but you only give them a chunk of the data. So they don't actually, every GPU gets like a little batch of the data. You see what I'm saying? So it's like, imagine in a train, you grab coal and that's one batch and then another batch. So you can distribute out the data because you don't really actually want to move the data between computers on the network. So you put a batch of the data in one computer with its own GPU. It performs all the operations. Then they aggregate and things like that.
Okay, so it's not like all the training data is stored in some giant server, like petabytes of data.
Initially, it might come in there as a staging area, but it's going to be divided into batches and things like that. Yeah, so a good analogy is like the train and coal. You give it a little bit, it learns from that. A little more, it learns from that. And essentially that, because yeah, it would be impossible to have enough RAM to give all of it at once. And we will actually do this semester at a smaller scale. But we'll divide our data in batches and learn this concept. Any other questions, guys? So yeah, so DeepSeek is pretty impressive. One theory is that they're saying is that they somehow figured out how to get more out of the GPUs. You know what I mean? So if a GPU could process so much, so for instance, one thing you might understand, you know how you can declare a variable and it's 32-bit, right? And Windows is 64-bit. So what does that mean essentially? When you create a variable in memory, you're using 32 bits of space and RAM versus 64. What they did is they reduced the precision to 8 bits. You see that? And that turned out to work still, even though it's only using 8-bit versus 32-bit. So, now they can store 4 variables instead of 1 in the same space. And it ran faster. And what they did in the GPU, I don't know. I mean, I'd love to know, but it's not clear how they got more out of the GPUs, but they were efficient. So essentially the news is that everyone can have a GPT now, a chat GPT for free that can reason. You can install it with something called Olama. You just have to go in and install Olama. It's very easy. And then say Olama serve deepseek, whatever it is, and then ask it questions. And it's going to help, it has the reasoning capability comparable to those of ChatGPT, which costs money, right? So it's pretty impressive and big development. So this area just doesn't stop. But anyway, any questions about that? All right, great. So yeah, so this, and the reason I guess why I bring that up is that this moves really quickly. Okay, so the field moves really quickly. The course covers some fundamental things. I will cover PyTorch, as I think is the state of the art in a basic class like this. But if you ever continue doing this, you'll have to keep up with it, right? And study on your own. Okay. All right. So yeah, for instance, Weka is 20 years old. I still use it, but PyTorch is only a few years old, and that's kind of what's being used. And then who knows with new modifications, what's going to happen. All right. So that being said, now let's move on to word problems. Okay. So I am recording, so I'm going to need the whiteboard for this. So let me. Figure out how to get. I think I need to stop sharing whiteboard. And essentially what I'm going to give you is like a procedure, like almost a template that you follow every time you have any problem. You just start to like, okay, this is this. You have a vocabulary of things like what are the features, what are the classes, what are the regression values, and then the shapes, the dimensions are critical. And that's kind of the way that you want to think about any problem that you want maybe to implement with machine learning. Okay. So that's kind of the idea. So let me make sure my pen works here. Red. Okay, yeah, so I just need to write like a few things. Like everything essentially, it's gonna be these two things. A matrix called X, which is gonna have, which is gonna be n by m, okay? And then a vector y, which usually will be, although this can change, n by 1, although this could be also k, let's say, okay? So essentially what I want you to understand here, when you're trying to, and you will see this because when we start writing code, the starting point will always be x and y. From x and y, I will start then doing a lot of machine learning things that we need to do. But when you have raw data or any problem, you have to figure out a way to arrive at x and y. Okay, and so that's the examples that we're going to do today. So to create new, add page. All right, so we're going to look at problems. So I need to go to Brightspace, and I have a lot of problems here. So I'll just pick one. So let me see. So I have, okay, let's usually the easiest problem to understand in machine learning is the one based on images. This is actually why machine learning kind of started with images, and that's where you really saw the first developments, progress. Then after that, it moved to language, right? Text and speech and things like that. And now you see it for time series forecasting, you see it for cybersecurity, you see it for other domains, right? Predicting molecules, right? And things like that in biology, medicine. But we're going to start with the simplest case probably, which is to understand images. So I have a problem here that says an image class. So number eight, an image class. So the goal here is you want to build a model. In this case, the model is an image classification model for the detection of Airbus A320 passenger jets while in flight. And that's the information. So when you approach these problems, you have to start making a lot of assumptions as well. All right. So usually in these problems, I'll say something like, for the following problems, and also you need to know, are they classification or regression? I covered this in the Weka class and the Weka lecture. So for these problems, identify and or define the following. What is the X matrix? What is the Y vector? What are the samples? What are the classes? Define a set of features, define the dimensions of X and Y, and indicate what they mean. Okay. I think if you can answer these questions, like quantify them, you can then take your raw data, put that data in the appropriate format, and then it's going to fit in Weka, it's going to fit in KNN, it's going to fit in your neural networks with PyTorch, etc. Right? So this is like the approach that you want to take. And actually also, by following this procedure, X and Y will be in something called the vector space model, which we will learn about, which is a geometrical representation of your data. So it's really nice, right? Because we understand, geometry, right? This is geometrical space. It's very intuitive for humans to live in 3D, for instance. And so that's why I start with KNN, because KNN is actually a geometrical machine learning algorithm. And so we're going to understand all of that just by doing this. Okay. And you'll learn how to create the X and Y and not realize that you're creating a vector space. All right. So let's focus now on problem number 8, an image classification model for the detection of Airbus A320 passenger jets while in flight. And so I'm going to go back to the whiteboard, and we are recording. All right, so we want to detect A320 while in flight, and it's a picture probably. So let's just start thinking about it. So in flight, so that means here's land, and you have maybe some camera pointing up in the sky, and it's taking pictures, not filming, to keep it simpler. Because if it's filmed, then it's what? How many images per second? It's like 24 frames per second. So that's a lot of computational power that you would need. So let's keep it simple. There's a plane in flight, right? And it's, airplane. So you take a picture of it, essentially, right? So that's what we know. So you would have then, you buy some camera, and the camera's just looking by the airport, just looking at the sky, and it takes pictures, right? So now we know that. So that's our medium, essentially. Remember, there's always going to be a medium in machine learning. If we're doing network security, the medium is what? Network packets. You see that? If we're doing malware detection, the medium is what? Files in the file system, right? If we're doing language, like speech, it's going to be the recording from a microphone, right? A WAV file. That's your medium. And you start from there. And this example is going to be the pictures that the camera takes. Okay. And we're trying to build a model that distinguishes between A320, finds A320. So I didn't really define the other part. So we want to start with something that's simple. You don't want to start with the most complicated case, for instance. So the most simplest case might be that you have some images that have an airplane, right? And some images that just have the blue sky and they might have a little cloud or something. Do you see that? So that's where you start. So then you have to think, okay, great. I know the medium, I know my images. I have to start answering questions about this. So for instance, do you use color images or do you use black and white images? It just depends on the problem. Obviously, color images might help you. But color images means that the image is actually 3 grids. One for the red, one for the blue, and one for the green. So this is RGB. So essentially, you have more data, okay? If it's black and white, then you only have 1 grid. Also, the dimensions of the image are important. Should you use 8K, for instance, for machine learning? Probably not. That's too big, right? 8K is, the resolution is too big. So you use 4K. No, that's too big. In fact, machine learning currently, the state of the art, believe it or not, is images that are about 1,000 by 1,000, and that's pretty big. If you run that on your computers, it's not, and I mean that's pixels, right? That's pixels. So your computer will not probably be able to handle it. We will see at the end of the semester when you use these models called ResNets, which is this idea of transfer learning. I think the resolution that they use by default is 220 by 220. Does that make sense, guys? 220 by 220 pixels. So grainy.
I'd say like earlier I was guessing that would be somewhere around 200 by 200.
Yeah, they are. Yeah, yeah. I used to say 300 by 300. Now I say 1,000 by 1,000. But the pre-trained models have this default size, and it's about 220 by 220. 144. Yeah, it used to be, and a lot of the data sets that we will use, like the classic MNIST, the images are 28 by 28. We see it blurry. What the AI sees, it looks at a pattern. As long as the pattern is there, enough signal, it's fine for it.
Oh, okay.
But yeah, we would see it blurry for sure. So there's one data set. It's called the Fashion MNIST and CIFAR 10 also, which we may play with at the end of the semester. If you look at those data sets, the images are super tiny and they're blurry for us. But actually, the machine learning algorithm is able to classify them really well. Okay, does that make sense, guys? So this I should say 220 by 220 by 3. So that's so it will support color, and this is kind of state of the art, but we'll probably, to train a model with this, we'll need the GPUs. So we'll need to use the cloud GPUs we have available. Because a lot of what we're doing with machine learning, and it kind of ties into what I was saying with deepseek at the beginning, our limitations are that we have too much data, we need a lot of data, but that requires a lot of computational power, resources that we don't have available. And I don't know how many of you actually have a GPU at home. Those of you that are gamers probably have one, an NVIDIA something, but not everyone does, right? So we need to rent them or use, here at the university, we have them for free in this cloud service, okay? But yeah, so going back to the problem, right? So my goal is to solve this problem. So as I said, whatever problem you give me, if you create X and Y, you have everything you need. You've answered all the questions. So that's where I need to go with this one, right? So we need to start making decisions. Okay, so we have a camera that takes pictures. One thing you want with your images is for all the images to be consistent. If they're not, you have to make them consistent. And that can create problems like aspect ratio if you stretch things, or cropping, which means you lose information or something like that. So I would say the simplest thing is just use the same camera that always takes an image of the same size. Got it? All right, so let's make a decision here then, because I didn't specify it in the problem. So you guys have to decide. Do you want to start with color images, or are you okay with black and white images? You feel color is better. Okay. Yeah, I agree. So There's going to be blue, white, the colors of the plane might be yellow that you never see in the sky. Okay, so then we know for sure 3 channels. Okay, so that means we have the grid 3 times. What size should the images be? Because you're taking you get the images, you can resize them, right? So you will learn in this class how to very easily with 1 line of code to resize your images. So what size should we use? You need to define that. Yeah, you can do 220 by 220. That may take a while to process, so you might want to start with something smaller. Like you get images that are 220 by 220, resize them to something smaller, test out your whole pipeline, and then modify it for the bigger image. So let's say, just so the numbers, because this is going to be, try to multiply 220 by 220 by 3. And you'll see this a large number. So let's do, just to keep it simple, for this example, let's assume they're 28 by 28. You see that? By 3. Because there's 3. So what I mean by this is there's 28 rows, right? And every row has a little column. These are called pixels in an image, right? These are called pixels. And what do pixels contain? They contain a value from 0 to 255, which indicate like this gray scale that you have for the R, the G, and the B, right? So if it's 0, I think it's like black. If it's 255, it's white, or the other way around, right? And then in between, you have varying shades of gray. Got it? Is that clear? So it's going to be numbers, right? Okay. So now we need to create X and Y. Now, later on, we're going to learn that there are models that you can feed data that is not, that is like a cube of data or a hypercube of data. We're going to learn that. But for now, we're just going to keep it simple to an X and Y that is basically a matrix. So this for now, because I want to teach a specific approach, all of our X's are going to be N by M, okay? And all of our Y's are going to be N also. So notice that these two match. And this can be 1 or it can be something else, okay? So everyone with me? So we've defined that. We've got color images. They're 28 by 28 by 3. All right, so now what is a sample? That's the next question. A sample in the matrix is every row. Okay, every row in the matrix X is a sample. And that's always the case. Okay, but you can define what a sample is. So for instance, a sample could be, if you're taking 1 picture every second, right? You could then say that a sample is the average of images per minute. So that means if you're taking an image every second, you would have 60 images that are the same size every minute, and then you just average them, and that's your image. Do you see that? That's a sample, because you need it that way for whatever reason. But for our example, let's just keep it simple. We're not keeping track of time, so the camera just takes pictures every now and then for whatever reason. Maybe there's a trigger, a sensor, or something like that of movement, etc. Whenever it takes that, that's a sample. So we're going to define that an image is a sample. Got it? All right. So now let's create a new page. All right. So we've defined, this is X. Sample 1, 1 image, sample 2, 1 image, sample 3, all the way to sample N. That's X. Y, if you notice, now hopefully let's think about Y. So if you notice, the size of the rows in X is the same as the size of the rows in Y. Why is that? Because in a supervised learning approach, every sample is going to be correlate it with something about that image. So for instance, what is our goal with this machine learning model? To detect A320 jets, right? That's it. So then if that's our goal, sometimes it takes a picture like that and there's a cloud. Sometimes it takes a picture and there's literally nothing. Sometimes there's a picture and there is in fact a A320. Other times there's like a bird and so on. Do you see that? So then you can, based on the problem, you want to identify A320s. So you can ask the question, is this an A320? No. False. 0. Is this an A320? No. False. 0. Is this an A320? Yes. 1. Is this an A320? No, it's a bird. 0. Do you see that? So these are the labels that are associated with the samples. And that's essentially what machine learning is. Machine learning is building models that, given something that looks like this, you want to say if it's this 0 or if it's the other thing 1. Right? That's a classification problem. The simplest. What's your question? Yes. So because you're defining it like that, right? And something like ChatGPT, what it's predicting is one of 50,000 numbers, which represent a syllable or a word, the next word in the sequence, for instance. Is the cat is on the table and is what? What's one possible word? The cat is on the table and is standing. Sure. Why not? Sleeping. Which one of those has a higher probability? Just based on experience in the world. How about singing a song? So that doesn't have any probability, right? So essentially, this is what models do. They predict something, a value. You can define whether you want it to be 50,000 things or just one of two things or some other thing. All right. But essentially, we are learning the machine learning algorithms in their simplest form. They are correlating machine. Given what I see here, it's this or that. And actually, what they're looking for is differences in the samples here, not similarities, but differences. Okay, got it. So again, all of this, you don't have to be able to solve these things necessarily 100%. It's about knowing the procedure and the terminology and what everything is, right? So we have samples. We know that each one of these is an image, but you're probably asking yourself, how am I going to fit an image in here? Because this is really just a row. But we've established that, some images look like this and they're zeros. Some images actually have A320s. They're 1. What if there's like a jet fighter in there? Actually a helicopter. Well, the definition of the problem is that we want A320s, right? Which is some type of a airliner. So this is also a 0. But who provides these zeros and ones? Well, it'll predict it, right? It'll predict it once it's trained, but you have to label it first, right? So that takes us to this idea when humans label things, basically what the algorithm is learning is how to think like a human. You see what I'm saying? So it's learning. So if a human says, oh, this is a 1, because it thinks that an A320 is a helicopter, then that's what it's going to learn. It learns from this data. Okay? So this is called annotation. And this still happens even in ChatGPT right now. People do provide some annotation and sometimes just very little. And the model goes from there and kind of understands what it's supposed to do. All right, so let's assume now there's another way to do this. Like it doesn't always have, let's say you have to collect 1 million of these because that's your requirement. It would be very expensive to hire people to spend all day looking at pictures and saying 0, 1, 0, 1, 0, 1. But nowadays you have these things called ADS-B, right? Which all airplanes have a transponder and they're actually sending like, hey, this is my number and I'm a Airbus A320. Versus other ones that might be a private jet and say, I'm not an A320. So actually you could build a camera that has a sensor that picks up that radio signal And whenever it gets it, it takes a picture and it knows, oh, this is an A320. So it can be automated sometimes. Sure. Or a person just looks at it and does it manually. It just depends on the problem. Do you guys understand? The point is that in supervised learning, there is some labeling going on associated with the images. Okay, great. So we've defined the samples. Let me ask you this question. How many samples? That's usually going to be dependent on the cost, right? So if you're at an airport, you have a camera with ADS-B, okay, you can collect a lot of images possibly. Say you're at O'Hare. But if you have to do this manually, then you would have fewer, correct? You would have fewer images because it would be expensive to collect. But you always want to have a number, just a reasonable number. So how many samples do you think you would collect? Because we want to determine what n is, so the number of rows. So just ballpark. What do you think? And you know, as we start looking at problems, what you'll understand is that there are problems that can have 1 million samples, and there are problems that only end up having 50, right? Because it's really difficult to collect the data. And so for this type of problem, detecting airplanes, let's say 50,000. Do you guys see that? It's just some number that you want to provide. It helps you out to reason out the difficulties of training this model, if it's going to be effective and so on. Got it? Everyone with me? All right. So what about here? So then this is also 50,000. And we know we've got zeros and ones. So that can be 0, 0, 1, 1, 1. So this is 1. The number of columns in Y is just 1 because you only need 1 to represent the data. The only thing that's left then is how many columns, right? How many columns here? These are called the features. What are the features? The features are the descriptors of the sample. Okay, so in an image, for instance, what are the descriptors of an image? If you don't do any post-processing or any modification, just the raw data, then what are the descriptors of each image? The pixels, right? And in this case, we know that that's why in the beginning I asked you, what is the dimension of the image, right? So we set, to keep it simple, is 28 by 28 by 3. So that is then we have that many pixels. So what is 28 by 28 is 784, right? And then 784 times 3 is what? Anyone? It's a calculator. No calculators. It's 784 times 3. 2,352. All right, so this is really important because these are the things that I will be looking for in the in exam problems, etc. Given that you decided that your images are 28 by 28 by 3, you have to tell me that you have 2,352. Do you see that? All right, so now let's summarize what we have. All right, and let me show you how an image is squeezed in here. This is usually called like spaghettifying, right? You stretch out the image, but we can look at a procedure. So let's remember 50,000 by 2352. We know the columns. Okay, so this problem has been essentially broken into 50,000 by 2,352 and 50,000 by 1, where this is X and this is Y. So when you start building this machine learning pipeline, you will have a folder full of images. The images, maybe you have one folder for the images that are 0, one folder for the images that are 1. That's a very common approach. You group the images like that, and then it's very easy to read them in your code. And basically what you need to do is once you start reading them, you're going to end up in memory with a variable called uppercase X and a vector, another variable that is going to be lowercase y. And that's going to be throughout the semester, basically the variable names that we're going to use. Okay, you always want to arrive at your X and Y. Once you have that, you can do a lot. A lot of the rest comes in, a lot of the machine learning pipeline. Makes sense? So we have the dimensions, and then now we set the features here are 2,352. So what you do is imagine we have so you guys wanted color images. So then I have RGB. Each one of these is 28 by 28. So what you can do is start with the first one, the R. And you grab the first row, right? And then you grab the second row, and you just concatenate them. And the third row, concatenate them, dot, 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 until you get to the last one, which is that one, right? And then now you have something here for this one, which is 784, correct? For R. And now you just repeat so this is R. Now you just repeat the process for G, another 784, and that's how we will eventually end up with 2,352. Make sense? So this would be our GB, and so the data is represented there. The key thing is you have to be consistent, right? You have to be consistent. So, let's say I pick column 100. That is always the 100th pixel of the R grid. You see that always for every single sample going down. If you get that wrong, garbage in, garbage out, right? Because the whole thing with machine learning is it needs to look at column 100 for all images and look at for instance, the differences. So now let's think about how it would work, right? So you have 1, 1, 0, 0. And everything, let's say it's determined by column 100. So then you would expect that if this is 0, then maybe the pattern is 50, 57, 200, 210. Do you see that? So they're not the same, but these on average are 50. These on average are 200. When it's closer to 50, it's more like a 1. When it's closer to 200, it's more like a 0. You guys see that? So essentially, that's what it's looking for, right? It doesn't really care. It's going to pick up really quickly that 50 and 57 is not the difference it's looking for. The difference it's looking for is like from 50 on average to 200 on average, because that's going to correlate to the objective of differentiating the images between them being a 1 or them being a 0. That's it. That's like the whole trick right there. Regardless of algorithm, that's the pattern that you're looking to find. Got it, guys? Does this make sense for everyone? So that's why I call these word problems. So I will always want to know, like you come to me with a problem, right? You're doing steganography or something. And I will ask you, how many images do you have? Are they color images? What is the sample? What are the dimensions of your X? What are the dimensions of your Y? You give me that information, we can quickly figure out what to do. You also, and one thing that you always want is for the data to be balanced. So what I mean by that is you want to have, if you have 50,000 images as we established, you probably would want to have, let's say 30,000 of not A320 and 20,000 of A320. So although they're not the same, it's a balanced data set. Yeah. But if you had out of the 50,000, let's say 1,000 are A320 and 49,000 are not, then I would say that's an imbalanced data set, and it's going to be more challenging to build a good model from that. Okay, so all these things you have to consider. Machine learning is highly experimental. Okay, so obviously there's lots of techniques, but as you encounter problems, you'll have to make assumptions and decisions. Okay, and that's problem number one. Any questions? Is it clear? We'll do a few more. Yeah, go ahead. Yeah. Yeah, it's because GPUs. So if you're using Weka, as you will do in the homework, you'll see that the multi-layer perceptron takes forever. And if I had given you images and you start, okay, I'm going to start with 220 by 220 by 3, but it's taking 2-3 days, then you're going to have to decide, you know what, I need to scale these down and see what, and speed this up a little bit. So a lot of the constraints, and that's why, again, the deepseek thing is so fundamental, because if you can really do, real AI with less, it's an amazing thing. But yeah, so performance here is crucial. Cost also. I mean, we have GPUs here, but if you have to go on the cloud, you're paying money. Any other questions, guys? All right, we're going to do another problem then. I always like to do a network security problem because it's kind of like a totally different thing. So we've done an image processing, which is like the easiest, I would say. The easiest to think about. We didn't have to do something called feature engineering. Like we didn't have to create features to represent the data. We just said, let's just use the pixels. All the pixels, as long as the images are consistent. But now let's look at a network security problem. So let me kind of want to